Having talked about the theory, now it's time to implement it. The problem in implementation would be to calculate the variables such as our stress and hardening parameters and our plastic strain increments at time t based on our knowns, like the stress and plastic, the hardening parameters at time 0 and our total strain increment. So these three are known to us. So at the beginning of the increment, well, these three are unknowns that needs to be solved. For a general increment, delta epsilon, it can be composed of two parts. One is purely elastic, and the part B is elastoplastic. The purely elastic part is basically loading from somewhere within the yield envelope to the edge of it. This state at C can be obtained through extrapolation. All the state variables like stress and hardening parameters at C can be considered as known to us. They are not difficult to be obtained. Once we obtain the state variables here and we obtain delta epsilon A, which enable us to travel from here to here, we then obtain delta epsilon B, and this is our total elastoplastic strain component, incremental strain component. So these three are known to us. So the problem is to solve these three based on what is known mainly here. The simplest approach to start with is to use explicit algorithm. Basically means that all the quantities that we need to calculate the three are evaluated at this point where we know everything about. Now we proceed with writing our tau t equals tau 0 plus delta tau, and then we can use the rate form of our constitutive law to write our delta tau equals the CE, our constitutive tensor, multiplied with the elastic component. So this elastic component equals the total strain increment minus the plastic strain increment, which is unknown to us. Then we can substitute in to this expression and break out the parentheses. We group these two together and form a new tensor called tau e. This equals to tau 0 plus the constitutive tensor multiplied with the entire loading increment. This is basically an elastic predictor. So we are assuming that the entire increment is elastic, and then we would arrive at somewhere here. Obviously, this point needs to be corrected because it's beyond the yield surface. So the yielding criteria is sort of oversatisfied. So you would have f larger than 1, larger than 0. And then the way to correct it is to basically add this plastic corrector part, which still needs to be determined. We can use a rate form which relates dot epsilon p with our dot lambda and the direction of plastic multiplier m here written in incremental form. Note that m is evaluated at c. So m in general is a function of g. G is a function of tau, and we evaluate this derivative at tau c. And for our associated flow rule, mc equals to nc, which is basically the gradient of f evaluated at tau c kc. Then we obtain our mc. We still need to calculate the delta lambda. We can use the formula that we obtained in the theory part to calculate delta lambda. Note that all these terms, like n and h, they are evaluated at this position, which is known to us. Once we calculate the delta lambda, and we calculate the mc, we then can calculate the tau t. This we would be able to be obtained. So this tau c is the elastic predictor corrected by a plastic corrector. So this would bring this point back along the direction which is determined at this point, because of minus sign is in the reverse direction, and this will not exactly arrive at the final ideal yield surface. So this is the drawback of explicit algorithm. We update the hardening parameters in the same manner. So the hardening parameter at time t is the values at time c plus the delta k. The delta k, we use a rate form, and it's directly proportional to delta lambda, and this function h is evaluated again at this point c. And then, as I mentioned earlier, the drawback with the explicit algorithm is that this condition is not enforced. So we are simply marching forward in time, but there are errors in the yield condition. And this means that our algorithm is only conditionally stable when the loading increment is small enough. So imagine that our loading increment is very big. So our elastic predictor is somewhere, let's say here. Now, if I were to make the correction, the plastic corrector would follow the direction that is set here. And from here, going in the reverse direction, you may not find the intersection between the direction of corrector and your yield envelope. Then your solution diverges. To improve upon this algorithm, to improve the stability and convergence of this algorithm, we could replace the explicit integration with an implicit one. Basically, instead of evaluating all these terms, all these functions at point C, we evaluate at time t. Of course, this would be unknown to us. So, in an implicit algorithm, we still have the elastic predictor, but our plastic increment is calculated by delta lambda multiplied with m evaluated at time t. So this still needs to be determined. And in the associated case, this is equals to the gradient evaluated at time t. And we can then plug in the expression, and we can symbolically at the moment obtain the expression of tau t, which is again a function of itself. Right? So this cannot be solved directly. When we plot this plastic corrector, the direction would correspond to the reverse of the gradient direction at the final intended solution point on the yield surface. But of course, this solution position needs to be calculated. Similarly, for the update of our hardening parameters, we also evaluate the function h at time t. And again, these are unknown to us. And our yield condition is strictly enforced at time t. So we have three equations. We can form three residues. The objective is to find the tau t and kt such that the three residues become zero, which then would correspond to satisfaction of this yield condition, this equation, and this equation. And by now you should be already familiar with the residues. They need to be solved in iterations. So using Newton-Raphson iteration at each integration point, we can solve for the solution to these residual equations. Bear in mind these are local iterations. They need to be performed within a global iteration at each integration point. So we can solve the problem by the usual full Newton-Raphson. We have our solution estimate at local iteration I plus 1 equals the previous estimate minus the inverse of this tangent stiffness matrix multiplied with the previous residues. This is an implicit algorithm, so it is unconditionally stable. We can afford to use larger increments. But the drawback is that now we need to perform local iterations within a global iteration at each integration point. So for metals, luckily, when we use von Mises yield condition, this return map algorithm can be much simplified into a radial return method. So basically, it's a simplified version of a return map algorithm which was presented earlier, and it can converge within a single iteration. So it's not too bad. Besides this explicit and implicit algorithm, there are in-between algorithms, such as the generalized trapezoidal, which evaluate the weighted average of residues between time 0 and time t, or the generalized midpoint algorithm, which evaluate the residues at a certain time between 0 and t. So these are less frequently used, and the implicit algorithm is the most robust and most widely used algorithm, and this is also the one that's implemented in Abaqus.